Hi, everyone. Dr. Meredith MacGregor is an assistant professor of astrophysical and planetary sciences at the University of Colorado Boulder. She also co-directs a Center for Astrophysics and Space Astronomy known as CASA. Dr. MacGregor received her BA through PhD from Harvard University in astronomy, astrophysics, and physics. Quite an achievement. She was a postdoc at the Harvard Smithsonian Center for Astrophysics. Her research focuses on the formation and potential habitability of planetary systems outside of our solar system. She is equally dedicated, and I mean this sincerely, she's equally dedicated to teaching excellence at CU and bringing girls along to consider careers in the STEM fields. She happened to grow up in Boulder, which is why she loves hiking and mountaineering, and she also plays violin in community orchestras. She is indeed a Renaissance woman. In her many achievements, Meredith evidences the potential women have to not only impact, but transform scientific endeavor. We also see the importance of women to the law and the elevation of Judge Ketanji Brown Jackson to the Supreme Court. We see it in politics and the once-in-a-generation Prime Minister of Germany, Angela Merkel, who brought peace and prosperity to Germany, unlike some other world leaders we're confronting now. For science, law, politics, and indeed Rotary, with Cassidy about to become our president, I would suggest an important measure of our success is having women in significant and transformative roles. They follow the tenets of the four-way test. So please join me and give a warm Boulder Rotary Club welcome to Dr. Meredith MacGregor.
Okay. Hi, everybody. It's great to be here. Oh, I'm supposed to stay in the light. Okay, I'm here. So this is really fun. As Meryl already said, I actually grew up in Boulder. And I remember back when I was in, I think, middle school, I won a poster contest for the Boulder Rotary Club, and I got to come to one of the meetings, and it was great. And I've already seen some people that I knew when I was growing up here. So this is a lot of fun to be here. So when Meryl contacted me, he asked me to talk about a wide range of topics, everything from what my current research group is doing, to the launch of the James Webb Space Telescope, to supporting women and diversity in STEM. So I have put together roughly 20 minutes of slides that will try and touch on all of those things. So we're going to go on a whirlwind tour of everything that I care about in space science and education, and then I'm happy to take questions and have a discussion with people about any of those topics. So that's why I kind of made up this title for my talk of exploring planetary habitability in research in the classroom. Okay, so let me make sure this is on and then click it through. So what my research group works in at CU Boulder is trying to understand how we form planetary systems. Our big question is, how do we form a planet like Earth, right? This habitable planet that we live on here and get to have Rotary Club meetings on. And I'm trying to understand how we go from this kind of early stage that we think happens at the beginning of planet formation, where we have a molecular cloud. It's this big cloud of gas and dust in space. Bits of this cloud collapse under gravity. They form a young, newly formed baby star, and that star is surrounded by this disk of dust and gas, and this is where we think we magically form planets. So somehow, in roughly 1 to 10 million years, we go through this whole process, we form some planets, and then most of that material is cleared away, and what we're left with is, something like our solar system. We have a star, the sun. It's surrounded by a system of planets. Some of them may or may not be habitable. And then we have remnant material, our asteroid belts and Kuiper belts, the things that didn't quite get all the way into the planets. And our research group is trying to understand this whole process. I want to try and go out and look at newly formed planetary systems, things that are still in the stages of forming, try and constrain them through observations to understand whether what comes out of this process may be other habitable planets. Okay, So I've said this word habitable a whole bunch, right? But what does that actually mean? So astronomers often make this very simple definition of habitability. We say that a planet is in a star's quote-unquote habitable zone if it is a distance away from that star, where, assuming it's an Earth-like planet, its surface temperature is about right to allow that planet to have liquid water oceans on it. So this essentially defines what we call, sometimes referred to as like a Goldilocks zone, where I have my star. If I'm too close to the star, it's way too hot, right? Any water is going to evaporate, it's going to boil off the planet. If I go too far away, it's too cold, any water is going to freeze. So there's some green region here, right, where I have the right surface temperature to allow for liquid water. And that is what, when you read in the news about habitability, people are often talking about when they say habitable planets. Okay, that's a useful definition, but it's a little bit too simplistic because there's actually a lot of other things happening on our Earth that make it a habitable planet, right? You can just look at our solar system and compare Venus to Earth to Mars, right? All of these planets are actually technically in this habitable zone. They're all a right distance from the sun to maybe have liquid water at some point in the history of our solar system. Clearly, only Earth is actually habitable right now. There's no liquid water oceans on Venus or Mars. So what are the differences here, right? So you can start to dig into that, and you might come up with a whole suite of other factors that are important here, right? Mars is smaller than Earth, so maybe planetary size is important. Earth has a magnetic field, right, that protects our atmosphere from getting stripped away. It allows us to have this atmosphere that protects our planet from the sun throwing out these giant flares and charged radiation and particles that impact the atmosphere of our planet. They make aurora, but they can also strip atmospheres, right? Maybe we care about plate tectonics. Plate tectonics are really important on Earth because they actually take carbon dioxide out of our atmosphere and sink it into the core and the mantle of the Earth, right? So they're helping us with the greenhouse effect. We might care about how fast the planet is rotating, right? And I can start digging into many, many, many more factors. So maybe this simple definition isn't quite good enough, right? And so where I wanted to go for a couple slides here is kind of trying to pick at two of these things that my research group has been working on. One, we think in our solar system, the outer planets, things like Jupiter, actually played a really important role because Jupiter actually moved around early in the solar system history, and it kicked a lot of comets and asteroids inwards that we think delivered water to Earth, right? So we actually think that Earth's water didn't form with it, it got delivered, and we need the giant planets to do that dynamical motion that moves that in. And then this ties into the volatile abundance. We can't actually have water or life if we don't have volatiles, things like carbon and oxygen and hydrogen and nitrogen actually incorporated in planets in the first place. So, what can we do to actually understand that? And nice thing is gonna work. Whoop! I just clicked through way too many slides. Okay, so the important question, if we tackle that thing about Jupiter first, we actually don't know whether there are other planets like Jupiter. In the 90s was the first time we discovered exoplanets, so we've known about exoplanets for a few decades now, and now we know of more than 5,000 exoplanets. We discovered through these techniques here on the left, where we're actually searching for planets by seeing their stars. And this is kind of what those planets look like. This is mass of planets, Earth in ratios of Earth, so this is Earth here. And this is the period, how long that planet takes to orbit the star, right? So here's Earth. Here's all of these planets that we've discovered. Here's some of our other solar system planets. We have Jupiter, Saturn, Uranus. You might notice something when you look at this plot, right? I always do this in class. I have students tell me what they notice when they look at this plot. We actually are not probing any planets that look like our solar system planets. Right now, all the planets we know about are really massive and they're really close to their host stars. And so I actually can't put our solar system into context because, I can't put our solar system into context because we just don't even know. So how would we look for planets like this? Clearly our current techniques aren't working. So one thing we can try and do is actually image planetary systems that are forming in really high resolution. And one of the telescopes that does this is this thing called ALMA, which is the Atacama Large Millimeter Array. It's located down in Chile. So here's where ALMA actually is. It's in the Atacama Desert at about 17,000 feet of elevation. And it consists of 66 antennas, these radio dishes, you can see them here, and here's a close-up, that can actually be picked up by this little caterpillar thing and moved across the Atacama Desert so that we can spread them out to distances of up to 16 kilometers. Okay, I just said a bunch of numbers and distances, and that might not mean a whole lot. What does that actually mean? So the ALMA antennas, all 66 of them, when we put them in their most compact configuration, would fit within the ellipse of the White House, small area. And if we spread them to their maximum distance, where we get the best resolution on planet formation, they would span the entire beltway in Washington, D.C. So that's huge. There's this giant array of radio dishes hanging out in the Atacama Desert in Chile at 17,000 feet of elevation. And ALMA has really completely revolutionized how we think about planet formation. Quick note, because I'm going to talk about different wavelengths of light during this talk, and that's not what people normally think about. So this is what we call the electromagnetic spectrum, which is all wavelengths of light, from long wavelengths on the right here to short wavelengths on the left. This little rainbow patch is what we can see with our eyes. So when we say light, most people think like whatever I see, but that's actually only a tiny piece of these, what's called electromagnetic spectrum, which is all the light that we could possibly study as astrophysicists in the universe. So ALMA is operating in this range over here, what's often called the microwaves. So that is, the wavelengths of those light. The space between those bumps is about a millimeter to maybe a centimeter. This is actually the same light that your microwave oven uses to heat food, but it's also produced by astrophysical sources, and we can study planet formation using this. Okay. So this is what planetary systems look with ALMA. These are real images of actual newly formed planetary systems. What we're seeing here is we're actually imaging those disks that I talked about on that very first slide. These are the disks of dust and gas that those planets are actually forming out of. And you can see that they have some interesting structures to them, right? They're getting carved out. These disks are what we actually call eccentric, which means that the star is not actually at the center of the disk. It's actually offset a bit. And so we think that that's actually getting carved out by potential planets. This is a little flip through of some newer, really high resolution observations where we can actually look, this is the same disk, but we're looking at one side versus the other side. And we have high enough resolution with ALMA that we can actually see differences in the width of that disk, on different sides of it. So we're probing down to, less than what's called an astronomical unit here, and an astronomical unit is the distance between the sun and the Earth. So we're probing down to the scales of our own planetary system here. Okay. What's fun then is we can actually use that structure to place constraints on the planets that are shaping those disks. So this is a system where we've actually imaged those planets. So there's a disk, and then inside of that disk are these 4 planets, which you can see as these 4 dots of light. And we actually have enough observations that we can see these planets orbit in real time. This is another solar system that's outside of our own solar system. And this is a disk where we actually think that there's a gap being carved out, and we can run simulations where we actually test out different planetary masses and put them in here and see what happens to the disk and try and reproduce our observations. And if we do that, we look at all these disks with all these beautiful structures. There's just tons and tons of these planetary systems with all sorts of interesting things happening in them. We can then infer this new population of planets. And so this is showing planet mass again. This is now showing semi-major axis. It's the same as period, right? Distance from the star. Here is all of these planets that we know about in gray. The black squares here are our solar system planets, and these colored symbols are the planets we infer by looking at the structure in these disks. And so all of a sudden, we're actually filling this out. For the first time, we're getting information on whether Jupiter-like planets are common in other planetary systems, and that's going to put a whole new perspective on how planet formation happens and understanding habitability in these systems. Okay, so I'm going to show a very complicated plot and use that to transition into JWST. So I don't expect everybody to understand everything that's in here. What I wanted to emphasize is that planet formation is even more complicated than I just presented it, right? I showed you these beautiful disks and the structure in them, and I said we can infer things about planets. There's actually a lot of chemistry happening in here. Different molecules are freezing out, becoming ice at different points in this disk, and so we can actually trace the chemical structure of disks. We can probe even closer into the star. And to really do that, we need to use different types of telescopes. ALMA is wonderful, but it's really good at kind of tracing these outer parts of disks where things are colder, because we're looking at longer wavelengths. And if we want to trace hotter material, we actually need to look closer in. And so this is where something like JWST, which we just launched on Christmas this past year, is going to be really important. Okay, so JWST, new topic. So this is a completely revolutionary space telescope. It launched on Christmas. At this point, it is at L2, this Lagrange point out from Earth, where it's going to be observing. It has completely unfolded itself. This whole telescope was basically folded like an origami telescope, and then unfolded over the course of the last several months. This whole mirror was packed up, and this sunshade down here was folded up around it to fit in the rocket. And then it launched and was released and then slowly unfolded. So now it is operational, and JWST is really going to revolutionize not just planet formation, which is kind of my passion, but also kind of our understanding of the history of our universe and how galaxies form and stars form and kind of any area of astrophysics that you can think of. What's really unique about it is it's in a completely different part of the spectrum than ALMA is. It's what we call infrared wavelengths. So infrared is basically heat light, you can think of, right? So we're all warm humans sitting in a room, and we are in fact giving off infrared radiation as we sit here. It's just heat. So anything like dust that gets heated up glows in the infrared. So this is trying to emphasize why we would care about that. This is a galaxy, shown in the optical on the left, which is beautiful. There's stars, but there's a lot of like hazy material here. That's all dust and gas. And it's hard to see through, right? This is making this look pretty opaque. The right here is the exact same galaxy, but now seen in infrared wavelengths, where all of that dust and gas actually glows really brightly. So all of a sudden you can see this like armed structure in this galaxy just by switching the wavelength of light that we look at. So what is JWST going to do for planet formation? So one thing that we hope to do is actually try and do more of this imaging of actual planets directly, what we call direct imaging. So to do this, astronomers basically use what's called a coronagraph, or a stop, to put it in front of the starlight and try and block out the light from the star, and hope that we can see the planets then around the star. So JWST is going to do this. This is actually an image from the Hubble Space Telescope, but we'll be able to do even better with JWST. And then one big area of research for JWST is what's called spectroscopy, which is maybe not the most intuitive of things. So spectroscopy, you can think about basically a prism, right? If we put a prism in front of a light, you get to see a beautiful rainbow on the other side of it, right? Because that prism is actually taking the light that comes in and it's splitting it by wavelength. So we split the light into all of its different wavelengths. So JWST has a spectroscope on it, which is going to split the infrared light out by wavelengths. And why is that interesting, besides that it shows rainbows? Well, these are two example spectra. So this is, brightness of light, intensity as a function of wavelength. The sun has this pretty continuous looking spectrum. There's not a whole lot of structure in here. This is the spectrum of a fluorescent light bulb. What's interesting here is that different atoms and molecules actually emit particular wavelengths. So you can actually, a spectrum of a light fingerprint what the atoms and molecules are making up that light are. And this is the same for astronomical sources. If I take a spectrum of a star or a planet's atmosphere, I can actually fingerprint it and basically tell you what atoms and molecules are in that astronomical object. So we are going to be able to do this with JWST, and these are simulations of what that might look like for a planet-forming disk. So this is a spectrum simulated for a planet-forming disk, and there's a lot of really interesting things here that we think are in disks, things like methane and ammonia, carbon dioxide, right? All sorts of complex molecules that we think are actually in these planet-forming regions. And the hope is that we're going to be able to go and look at these systems, take these spectra, and actually tell you, what is the abundance of these different molecules in these planet-forming environments. And then we can do that for exoplanet atmospheres as well. We can do the same thing. Here, this is showing things that might be in an exoplanet atmosphere, things like water or methane or ozone, things that are in our Earth's atmosphere and are because Earth has life on it. So we're stepping into this new world here with JWST where we're going to be able to look at the abundance of these molecules in their planet-forming environments, look at them on planets, and then start to actually have the information to think about not only whether that planet is habitable, but whether that planet actually has life on it, right? This is where astronomers talk about looking for biosignatures. What could we detect in an atmosphere that would tell us definitively that there's life on that other planet? Okay, so so the last thing I want to show on JWST here, right, is this is actually the first image that's been taken by JWST. So this is a real image that was taken and released from JWST a couple weeks ago. This is actually a star. The spikes here are what we call diffraction pattern. It's actually because of the lens structure of the telescope. So this is a star. And every single one of these things in the background here is actually a galaxy, which I think is even more interesting than the star. I mean, the star shows you that the mirror is actually aligned and that we can in fact point this telescope and we can do science with it. But then, you know, you could see just in this one little image all of these galaxies and the structure of all these galaxies. So stay tuned, because in the next couple of months, we're going to move from the commissioning, which is just proving that the telescope works, to actually taking real data, and you'll start to see real science results coming out of the telescope. So I'll use this to transition into talking about briefly education and why I care about teaching and diversity in STEM. So this is, the bottom of this is a timeline of sort of major telescope launches in astrophysics. So it starts in 1990, which is when the Hubble Space Telescope was launched. And Hubble is still operating now, you know, more than 30 years later, doing amazing revolutionary science. We didn't know about exoplanets until 1995, roughly, right? We chose, astronomy does what's called a decadal survey, where the National Academies actually runs a panel to decide what the priorities are for all of astrophysics for the next 10 years. So JWST was chosen in the decadal survey that happened in 2000. So I graduated high school in 2007, so this is a while ago. And we launched it in 2021, and we're now doing science in 2022. And so I've overlaid my own fun pictures from my childhood here, right, to emphasize this point that, like, you know, back in 1995, when we just learned about exoplanets, I was doing homework with my cat, right? Here's me doing science fairs in high school. I graduated with my PhD in 2017. So the time scale on which we do this research is decades, which is like lifetimes, right? For people, it's careers. It means that the telescopes that I'm trying to design now and will get launched in the 2030s or 2040s, you guys will be using, right? Because that's the timeline it takes to build instruments like this. And also the timeline on which we're completely changing the field. So people always ask me, like, what do I think the coolest thing JWST is going to discover is? And honestly, I don't even know. Because when we launched Hubble, we didn't even know that exoplanets existed, right? We didn't know there were planets around other stars. Hubble has done a huge amount of research in this, but when you built Hubble, that was not a science goal, right? So I can tell you things that I know it will do, but probably we're going to discover something that we have no idea about, and that's going to be what's revolutionary for JWST. So with that in mind, right, then science becomes about trying to educate people, right? It becomes about trying to train the next generation of people that are going to be using JWST and whatever the next telescope is, who are in elementary school now, who are maybe not even born, and trying to engage a community. So I wanted to highlight kind of two different things here. One is sort of like, I take two paths to doing this, right? One is outreach and like community engagement and teaching kids when they're not in college, right? Before they're turned off of science because they had a terrible physics teacher at some point. So before I came here, I was a postdoc in the Carnegie Institution in Washington, D.C., and I led a program there through Carnegie that's called the Carnegie Academy for Science Education. This program basically partners with public schools in Washington, D.C., and runs a free Saturday science school for any middle school student in the entire D.C. area. And so it meets in sort of 3 terms in a year. Each term is roughly 6 weeks long for 3 hours every Saturday. And it's entirely volunteer driven. And so when I was a postdoc, I designed a curriculum to basically teach astrobiology and exoplanets and planet formation to these middle school kids. And so we wrote this curriculum and then taught it over a course of a year. And the added, benefit of this is that CASE actually partners with the schools and teachers as well and brings in teachers to, take curricular things that we do in these Saturday science schools and then teach it to the teachers so that they can go bring it back to their classrooms. So I loved working in this program. It was a really unique program. I got to engage with 30 middle school students every Saturday and teach them about space. And, they're in schools where they never have a chance to learn this, right? The DC public school system is very different than the Boulder public school system. And then stepping all the way forward, right now I'm a university professor. So I think about this from the side of educating college students, which I think is important to talk about too. And CU is a really unique place, which I don't think everybody always appreciates. We have the largest astrophysics major in the entire country. We have about 400 students who major in astrophysics at CU. So when I go and I teach introductory astrobiology or something, I'm teaching it to a 150-person lecture hall with the same microphone that I get to use today. And I think that's a really unique opportunity, and I'm not sure as a department we've fully figured out what that means or the power that we have as a department to actually engage with these students, because we get to teach astrophysics to 200 students, and that's just our majors. There's many more students who pass through our department who are just taking general education courses. So something that I'm spending a lot of time thinking about now is what are we actually doing with these students, right? We're not going to turn all of them into astrophysics professors, but how are we mentoring and engaging these students and learning what they're doing after graduation and moving them into careers doing a variety of other things that are not space science? And who are we losing, right? So I put these two plots in, which I grabbed. You can actually go on the CU website. All this is public data, because it's a public university. You can go and track, the APS department and split students based upon different groupings, right, and plot their GPAs. And so the top plot here is splitting out, underrepresented minority students and showing how GPAs track in our department over time. This is spanning 10 years or so. And then, this next plot down here is tracking between not first-generation college students and first-generation college students and what their GPAs are in our department. So I would look at these plots and note that maybe there's some things that we're not addressing as a department here, and if we really want to we can do the same for women. We want to, think about this timeline of decades to build space telescopes and shape the field of astrophysics and science. Then we need to, not only engage students younger, but also think about our college students and how we can better support them, because we lose people out of this pipeline at all stages. So with that, I will put up a brief kind of summary slide with a pretty picture on it, and I'm happy to take any questions.
Great. I'll go to anybody. Do any of the young people who are joining us today have any questions? Thought I'd ask you first. Oh, here you go. Stand up, Caitlin. There you go. Good job.
Do you guys have any planets that you think could be habitable for humans in the future?
Oh, so I think I heard you. Do we have planets that we think could be habitable now? Yeah. So yes, largely that comes from this broad definition. So right now there are probably a few dozen planets that we know of that meet sort of these basic criteria, in that they are roughly the size of Earth and they exist in that kind of zone, this habitable zone where they could have liquid water. So yes. I can't actually answer all those questions, but I have no way to know if there's plate tectonics on any of these planets, right? That's not something we can study on exoplanets. But there are candidates. There's not a lot of them, actually. The vast majority of those planets that I showed on those plots are very different. The closest potentially habitable planet is Proxima Centauri b, which orbits the closest star to us, actually, besides the sun. So Proxima Centauri is only 4 light years away. That means light from Proxima takes 4 years to get to us, and that's the closest star we have with the closest planetary system, and it actually has a planet that is roughly Earth-sized and sitting in the habitable zone of that star.
Thank you. It was understandable, at least to somebody who had a science background. 50 years ago, when I was still practicing historian of science, one of the things I was interested in was science and religion. I still am. But every religion has a creation myth, and some of them have a destruction myth. So my question is, if you can do it in 3 hours, what is the current astrophysics explanation of the beginning of the universe and the end of the universe?
Okay. That's a big question. Okay, so I'm going to give a completely inadequate answer to that. The picture that we have is that this is the universe started in what's called a Big Bang, where within, tiny fraction of a second, the universe basically went from nothing to existing in this period of rapid expansion that's called inflation. So that's the start of the universe, right? And then the universe continues to expand outwards from this point. And as it expands outwards, it starts to cool. And so you go through these different stages where the universe actually cools enough that you can start to form protons and neutrons and electrons and therefore atoms. And then they can start to form elements. And you go through this period of expansion. You keep expanding outwards. Eventually, you start to form stars. The stars actually reheat the universe. It's this period called reionization, where you reionize the material because now you've turned on these hot stars, and slowly you start to form galaxies, right? Underlying all of this is the assumption that there's some kind of density field that underlies the structure of our universe, and that density field has fluctuations in it, and so we actually form galaxies and structure along these filaments. So if you look, there's some really beautiful surveys of galaxies, in these, the Sloan Digital Sky Survey has surveyed. You can actually see this filamentary structure where the galaxies in our universe all kind of lie along these threads, and then there's big areas of empty space that are called voids in between. In terms of the end of the universe is still expanding, so we can actually look at distant galaxies and measure their velocity relative to us, and everything is moving away, and it's moving away at an accelerating rate. So the expansion, we think, is actually accelerating. And then you get into the debate of how the universe would end, which, falls into sort of two main categories. And it depends on how much material there actually is in the universe, which we don't know. The universe will either just continue expanding forever, and everything will just stretch apart, which is interesting to think about, right? Because then we'd be left here in our solar system, and we wouldn't see anything else, right? Because you would eventually expand everything away. Or the universe will eventually slow down and reach some turning point, at which point it will turn back around and start collapsing in on itself. That's what often gets called the big crunch. Right? In which case the entire universe would crunch back in on itself in a rapid deflation and then smush into, non-existence again. And we actually don't know the answer to that.
Dr. MacGregor, thank you so very much for speaking to Boulder Rotary today. Very thought-provoking questions that you've presented to us. And we're so thankful for the time that you've taken to share this with us. In honor of your presentation, we would like to contribute 100 doses of polio vaccine to the Rotary Polio Plus campaign. Over 40 years ago, Rotary decided to work with other organizations to eradicate polio from the earth. And we are very, very close. There are only a few countries that still have polio. And we've gotten it down to a handful of cases each year. So we hope that within a few years, Rotary will be among the organizations that have eradicated polio. So thank you so much for your talk.
Thank you. That's probably the largest impact any of my talks have ever had. So